All right, we left off, I think, right around here where we had we determined our rate law, and it was a first order with respect to the H2O2. It was a first order with respect to the I minus, and it was a zero order with respect to H plus, and anything raised to the zero is 1. And so our rate law was rate is equal to K, concentration of H2O2, times the concentration of I minus. And then we have to solve for the rate constant K. So if we go back and we have 4 different experiments, and again, when they're in the book, they are all 4 going to be exactly the same. K is a constant. Again, when we do a lab on Thursday and we're calculating K, we're doing an average K. And you can do it all 4 times and you'll get the same answer all 4 times. When you do it in lab, there's all kinds of errors that you're going to have in lab, and you will not get the same answer in lab. We're doing it 3 times, and so you would then take an average. All right, but if we take experiment 1, and we take our 0.01, our 0.01, and our 1.15 times 10 to the minus 6, we plug it into our equation. All right, the 1.15 times 10 to the minus 6 is equal to K, and this was 0.01, and this was also 0.01. So again, you would probably want to do the math in multiple steps. Don't make a simple math error and get this wrong, so you can show all of your work. So to get rid of the numbers on the right, you divide both sides by the 0.01 and the 0.01. All right, and so you can show that they cancel out, and then you're left with K. Then you push the buttons on your calculator, and you get 1.2 times 10 to the negative 2 is equal to K. Now we need our units, and so here the units are given. All right, so our rate units are always the same. For rate, it's molarity per time. And it is, in this case, molarity per second. All of your concentrations, when you have a bracket, anytime you have a bracket, this means it's molarity. All right, so a bracket is molarity. And so your 0.01, that's molarity, that's molarity, that's molarity, that's molarity. Over here is where it matters. Here's molarity, and here is molarity. And so you see that the molarity is going to cancel molarity, and you end up with 1 over molarity times seconds. And that is your units for this second order reaction. So first order with H2O2, first order with I minus. This is a second order overall reaction. All right, for every second order overall reaction, your units for K will be 1 over molarity times second. All right, so your units for K. All right. If it's first order, the 2 most common orders that we're going to deal with is first order, where it is going to be 1 over seconds for your units for K. If it is second order, it is 1 over molarity times seconds, which is what we got in our problem here. If it is a third order, then it's going to be 1 over molarity squared times seconds. If it is fourth order, then it's going to be 1 over molarity to the third times seconds. If it is a zero order, then it's going to be molarity per second. All right, and I don't think you're going to have any, well, you might have a fifth order, doubtful. This should cover every order that we're going to have, but again, it might be a fifth order. If it's a fifth order overall reaction, 1 over molarity to the fourth times second. So you should see the trend. So when we go from first order, second order, third order, fourth order, fifth order, we have a molarity being added to the denominator. All right, so it's molarity here to the 0, molarity to the 1, molarity 2, molarity 3, molarity 4. So fifth order is molarity to the fourth, second order, molarity to the first. So it's going to keep going that way. But that should include all of the orders that we're going to cover in this class. And so you can know the units for K, and the two that I would say you must know. You can calculate the other ones when you need them, but these should be converted to memory, and that is your first order and second order, the most common ones that we're going to do. So if K is given and it says K is 1.2 times 10 to the minus 2, 1 over molarity times seconds, what you can say immediately is it's a second order reaction. You know the order of the reaction if they give you the units for K. All right. In the problems in the book, they will say in this first order reaction, the K value is this with the units. On the test, most likely it's not going to tell you the order of the reaction. It's going to give you the units for K, and so you would need to know that if the units for K is 1 over seconds, that means it's first order. If the units for K is 1 over molarity times second, then it is second order. Those are the two that you must know. We use them all the time. All right, so here is the slide that says for a zero order reaction, your unit is going to be molarity per second. Note, again, how they will write it. All right, so they can write molarity per second, or they can write moles per liter second. You need to know that that is the same thing. For first order, they will write 1 over second, or if they write seconds to the minus 1, you need to know that that is exactly the same as a 1 over second. All right, so most people get that down. Now, it's the second order units that will start to confuse people. You have 1 over molarity times seconds. That's how it's normally written, but it could be written as a liter per mole second, and that is exactly the same thing because a molarity is moles per liter. That's in the denominator. You invert and multiply, you end up with liters on top, moles on bottom. And so if you see it as a liter per mole second, you need to know that that is the same as 1 over molarity times second. And note that they have the, so when I write it like this, molarity times seconds. They put it in parentheses, all right, to be sure that, especially when you're divided by is this way, you don't need to do that. But when it's this way, you need to put in the parentheses. All right, so you know that the molarity and the seconds are in the denominator. All right, so if you know the rate constant, you can deduce the overall rate of the reaction. What you need to know is the K value for first order and second order. The other ones will not be required for you to know. You should know them. But first order and second order are required for you to know that once you're given that unit of 1 over seconds, you immediately go to first order. Or if they say it's first order and here's a K and they don't give you units, it's going to be 1 over seconds. The default time is going to be seconds. If it is different time, they must be very clear that the units are 1 over years or 1 over days or 1 over whatever time they're going to use. But the default is always per second. All right, so now we're going to do the integrated rate law. So now that means calculus. So if anyone's had calculus, you know what an integration is, I think. You know what a derivative is? Integration is the opposite of the derivative. It's sort of like if you know multiplication, well, then you know division. So integrated rate law. So we're only going to do the integrated rate law. We might do it for the zero order, but first and second order, that is 99% of the questions for the integrated rate law. All right, so let's do a first order. If we're doing a first order reaction, I'm going to say that A goes to products. All right, but I already told you it's first order. So now you know it's first order. You know the units for K, 1/seconds. All right, and you know the rate law, because I told you it was first order. And so we know that the rate law is K times A to the first. Again, you don't need to put the 1 there. All right, so I told you it's a first order reaction. There's one reactant, and it's A going to products. And so your rate is equal to K times the concentration of A. All right, now to find the rate, since I didn't give any letters for the products, I just have A going to products. The way we're going to look at the rate for this reaction, and we're going to do it in very, very small changes, we're going to look for the disappearance of A over a short period of time. All right, so we had delta A over delta T. If you have the delta A over delta T, these are for large changes, all right? When we're doing small changes, now we're talking about the tangent line, we're talking about calculus, we're talking about integrations, all right? So this is for the small change. All right, so what we're going to do then is, this is how we're going to find our rate. Plug that in for rate. So we are looking at the disappearance of A over time, and that is equal to K times A to the first. All right, so then we combine like terms. So we're going to take our dA and then divide that by A. All right, so we're going to divide both sides by a negative A. All right, so the negatives here cancel, and so we have the negative that's going to be on the right. And then we're going to multiply both sides by dt. All right, and so the dt is gone here, and so you end up with negative k dt. So if you've done an integration before, you have this. Again, you do not have to do integrations in this class. And we're going to integrate from 0 to t. And then we're going to integrate this side from our initial concentration of A to the concentration of A at time t. All right, and so then we're going to have our integration. So anyone know the integration of dx over x? Anyone? It's a special case integration. No one needs to know this. I'm just interested to know if anyone knows this. Integration dx over x? No. That is the ln of x, natural log of x. So dA over A is the natural log of A. All right, and from the initial to A at time t, not sure if I gotta ask Kirchhoffer if he does integrations in Calc 1. All right, and then integration of dx. Anyone know the integration of dx? That is just simply x, and so then you have your negative k here, and then you have your t integration limits from 0 to t. All right, so when you are done doing your calculus, having all that fun with your calculus, you end up with the ln of A at time t minus the ln of A initial is equal to negative KT. All right, and so you don't need to know how this is obtained. This is how it's obtained. You don't need to know that. But what you need to know is how to use this equation and when to use this equation. This is the first order rate law. So you only use this integrated rate law when the K value has the units of 1/2, or the problem says it's first order, or in some cases, both times. So you can only use the first order integrated rate law when you have a first order reaction. All right, so they have it here, so then they don't show the calculus and the integrations. They just say using calculus, you get this derivation. So note, the way I had it was the ln of a at time t minus the ln of a initial. And so this is a log rule that you should know. When you have the subtraction of the logs, that is then dividing them. So if you're adding the logs, that is then multiplying them. So you have your log rule. So that is equal to the ln of a at time t over the ln of a initial. And this is where parentheses would be very handy, because if you take the ln of a at time t and then divide by the ln of a, that's wrong. If you take the ln at divide by a, so that's wrong. You have to get that division first, ln of that division. And if you have a decent calculator, when you push your ln button, the first thing that pops up is a parentheses right after that ln button. So they automatically put it in parentheses for you. But if you don't have a calculator like that, you will want to do that division first, then the ln of that. All right, so this is your first order integrated rate law. All right. Let's see, let's put it, okay, and in the other form, we're going to solve for the ln of a at time t. And that is equal to negative kt plus the ln of a initial. Put a line through there, but all right. All right, so this is in the form y is equal to mx plus b. So when you are going to graph your first order rate law, you're going to graph on the y-axis the ln of a at time t, and you're going to graph time on the x-axis, and you're going to have a negative slope. So this is a straight line, and so you're going to have a line that has a negative slope, where your slope is equal to negative k. And then your y-intercept is the ln of a initial. All right, so the 0 means at time 0, which means you haven't started the reaction yet. That means that's the initial concentration that you are starting with. All right, and so you can have the equation written, the two ways that you'll see it most is this way, or in the form y is equal to mx plus b. Those are the two ways. They're exactly the same. You should know your log rules. When you subtract two logs, you can combine them, divide the two numbers, and then take the ln of that. So you should know your log rules for that one. Here is another calculus. All right, so now it says here that it is second order. All right, and we only have one reactant going to products. And so we know the rate law. So the rate law is rate is equal to K, A, now it's to the second. So it tells you it's a second order rate law. There's only one reactant, reactant A, going to products. And so now it has to be raised to the second, because they told you it was a second order rate law. All right, so we're going to look at the rate the same way. It's right here. So we look at the change in concentration of A, the disappearance of concentration of A over time. Then we're going to combine our like terms, and we're going to have negative dA over A squared. And that is equal to KT. And then we actually do the calculus. We integrate it from the initial concentration to the concentration at time t, from 0 time to time t. And then when you integrate dx over x, you get 1 over x. All right, and so the integration is, for that, a negative 1 over x. The negatives then go away. And the second order integrated rate law is right here in the form of y is equal to mx plus b. So if you're going to graph a second order, you have on your y-axis 1 over a at time t, and you have time in your x-axis. Now here k is positive, you have a positive slope, and so your slope is equal to your rate constant k, and your y-intercept is equal to your 1 over your concentration of A initial. All right, so you will have to know what to graph in order to find a first order versus a second order. So if you just have data, you will graph the data. You'll graph the 1 over A at time t versus t. You'll graph the ln of A at time t versus t. One of them is going to give you a straight line. The other one is not going to be straight. There's going to be some curve to it. The one that gives you the straight line, that is the order of that reaction. All right, zero order. So when you're doing zero order and you have A going to products, then you're looking at the disappearance of A over time, and that is equal to just K, because the rate law is rate is equal to K, A, zero order, raised to the 0. Anything raised to 0 is 1. All right, and so you end up with dA is equal to K dt, so negative K dt. So we integrate it from 0, from A initial to A at time t, and from 0 time to time. Are they not integrating this? Yeah, okay. All right, and so then you, for your integration, you have x. All right, if it's dx, you would have x. So here is A from your initial concentration to your concentration at time t is equal to negative K, and again, you have your t from 0 to t. So you have A, concentration of A at time t minus concentration of A initial is equal to negative KT. And then when you solve for A at time t, you have negative KT plus your initial concentration of A, which is what they have right here. All right, so here is your integrated zero order rate law in the form y is equal to mx plus b. And so if you're graphing this one, you're graphing the concentration of A at time t versus t, and you're going to get a negative slope. All right, and so here your slope is equal to negative k, your y-intercept is equal to your concentration of A initial. All right, so you have your first and second order. That's going to be 99% of your questions. The other 1% will be a zero order questions. There's very few zero order reactions that we're going to talk about, but there are some. All right, so here they give us 2 pieces of information that they only need to give us 1. And the one that I'm going to leave out is this one. So the question on the test will say the decomposition of N2O5 to NO2 and O2 has a rate constant with a rate constant of 4.80 times 10 to the minus 4 per second at 45 degrees Celsius. So when I see the units for K as 1 over seconds, then I know it's first order. All right? And so when I have first order, I know that I am looking at the integrated first order rate law. So I'm looking at the ln of A at time t is equal to negative kt plus the ln of A initial. All right, so I know it's first order. I have to go to my first order equation. All right, and so then you go to your questions. At the initial concentration, all right, so now we're talking about A initial, all right, so, but they give us the actual compound, which is the decomposition of N2O5. So to be more specific, it is N2O5 initial concentration. All right, and so that is 1.65 times 10 to the minus 2 moles per liter. What is the concentration after 825 seconds? And so this is my T. All right, and so we're looking for the concentration of N2O5 after 825 seconds. All right, so we just plug that into our equation. We have the ln of A, well, let's be specific, N2O5, that's what we're looking for, at 825 seconds. All right, so that's what A sub T is. That is our reactant, and this is the time. Our reactant for this reaction is N2O5, and we're looking at it at 825 seconds. And that is equal to negative KT. So negative, they give us the K value. That's how we knew it was first order, because I crossed out it was first order in the problem. 4.80 times 10 to the negative 4. Why, I just put a giant dash through that. All right, so it's negative 4.80 times 10 to the minus 4, 1 over seconds. All right, and then the time, that gives us 825 seconds. All right, so the seconds, cancel the seconds. That's why your units for time are very important. If they would have given you minutes, if they would have given you hours, you would have to convert that to seconds. So that's seconds, 1 over seconds, cancel seconds. All right, so the key here is the time must be the same so that it will cancel out. It can be the same as in minutes or hours or days or years or whatever. It just has to be the same. Most of the time it's going to be seconds, but not all the time. And then plus the ln of the initial concentration that they gave us, which was 1.65 times 10 to the minus 2. All right, so then you just push the buttons on your calculator and you get your answer. All right, so we have all right, so they plugged it into this one, which would be getting the exact same answer. So they have their unknown as the concentration of N2O5 at time t. They plugged in their initial concentration. All right. So they have that. So for that, all right. So to solve. So when you have it, the way we did it, we're going to have a number and we're just going to have the ln of this, the way they do it. What you need to know is how to get rid of your ln. In order to get rid of the ln, you push your e to the x button. E to the ln, and it just goes away. And what you have left is your N2O5 here. Divided by the 1.65 times 10 to the minus 2. And then you're also pushing the e to the other side, which is e to the negative 0.396. All right, to get rid of the ln, you push your e to the x button. All right, and so then this is 0.673. All right, so then you have to then solve. Once you know you get that number on your calculator, then multiply both sides by the 1.65 times 10 to the minus 2. and then you have your concentration. Now, when you get your answer, you need to check what did you start with, because it has to be less now than it was before. We are doing the decomposition of N2O5. All right, and so here is our initial concentration. It is in decimal form, 0.0165. So that is our initial concentration. And so after time, it's decomposing, and now it's down to 0.0111. All right, so you'll definitely want to make sure that you push the buttons right. You have an answer that is a possible answer. It's decomposing. The concentration must be going down. All right, the next question was, how long would it take for a concentration of N2O5 to decrease to 1 times 10 to the minus 2 from an initial value given? So we still have our initial value of 1.65 times 10 to the minus 2. All right, so we have our initial 1.65 times 10 to the minus 2. All right, so this time they don't give us a time, they give us the concentration after some time. There can only be one unknown. The first unknown was, what is my concentration after 825 seconds? The second question, B, is my concentration started here, it's now here, how long did that take? And so we're solving for time. All right, and so we have our equation, and we'll use the one that they've been using, which is your ln of A at time t, 1.00 times 10 to the minus 2, divided by the initial 1.65 times 10 to the minus 2. When you're using this equation, make sure you have your parentheses. You are dividing those numbers, ln of the division of those two numbers. If you do the ln of 1 times 10 to the minus 2 and then divide by 1.65 times, it's going to take the ln of 1 times 10 and then it's going to divide by 1.65. That is not what it's telling you to do. You have to get that division first. You're taking the ln of that quotient. All right, and that is equal to negative kt. So negative k given 4.8 times 10 to the minus 4, 1 over second, and t. So now all we have to do is get our answer for t. Now note, since we have the units of 1 over seconds, and what we're going to do to solve for this is we're going to divide both sides. We're going to divide both sides by negative 4.8 times 10 to the minus 4, 1 over seconds. We're going to divide both sides by 4.8 times 10 to the negative 4, 1 over seconds. And so when you divide by 1 over seconds, you invert multiply. Your units are then seconds. All right, and so you can never have a negative time. So the ln of this number, that is a fractional number, it is less than 1, is going to give you a negative number. And then you're going to divide by a negative number, you're going to get a positive time. If you ever get a negative time, you have left out a negative somewhere. You can never have a negative time. All right, and so then we will get our time. So our previous answer for this was 0.0111. All right, so what we can do from that is see that it's going to take longer. So it went from 1.65. Now we have to go down to 1.00. It took 825 seconds to go to 0.0111. So your number has to be greater than 825, but pretty close to the 825, not like twice that much. So we push the buttons, we should get somewhere in the 1,000 area. And so we push the buttons and we get 1,040. All right, so here is solving for, so this is your ln. Again, they're not putting the parentheses. If you push this in your calculator, you might get it wrong. I would highly recommend putting in the parentheses, making sure you're dividing those two. Those are in parentheses. Again, your calculator should, as soon as you push ln, give you a parenthesis. But if not, make sure you put it in. All right, and so you have your 1,040 seconds. The 3 sig figs, you would put it in scientific notation, 1.04 times 10 to the third seconds. All right, so if you don't know how long that is, you would like to know how long that is, then of course you would then take your seconds to convert it into minutes. You would have to then divide by your 60 seconds in a minute. So when you divide that by 60 seconds in 1 minute, then you see that that is 17.4 minutes. Everyone knows how long 17.4 minutes is. Not everybody knows how long 1,040 seconds are. A lot of times they'll give your answer in something that is more understandable. All right, now half-life, another very important and not that difficult of a subject is half-life, although you're going to have different rules for first order, second order, and zero order. All right, so half-life is simply defined as how long it takes for half of your concentration to be gone. How long does it take for half of it to decompose? So if you're starting with 2 molar, how long does it take to go to 1 molar? If you're starting with 1 molar, how long does it take to go to a half a molar? How long does it take for half of the reaction, the reactant concentration to decrease? All right, so that is the half-life. So anytime we're doing the half-life, we will call that as a T sub 1/2. So that just indicates that we're talking about a half-life. All right, so we have our initial concentration. Now our A at time T, we are looking at that when it is exactly 1/2 of the initial concentration. All right, so that's what we're going to do for our substitution. A sub T, we want to know how long does it take for that to get to 1/2 of our initial concentration. All right, and so we just do a substitution. And when you do that, you have your ln of A at time T over A initial, and that is equal to negative KT. All right, so now we're going to do half-life. So now I have the ln of 1/2 of concentration of A initial divided by concentration of A initial is equal to negative K and T 1/2. And so you see that your initial concentration of A cancels your initial concentration of A. And so you end up with the ln of 1/2 is equal to negative K T 1/2. And so you can actually get on your calculator, push the ln of 1/2, and that is a negative 0.693, a negative 0.693, and that's equal to negative KT 1/2. So divide both sides by a negative K. What you get, all right, and so this is the first order. All right, so I use the integrated rate law, first order, LNs, that is for first order. And so you would need a first order half-life. And now you have your answer once you divide by a negative K. So your T 1/2 is equal to 0.693 divided by K. So first order is very simple. If they want the half-life of any first order reaction, you simply take your 0.693 and divide by the rate constant K. And that will give you your half-life for first order. All right, and if you did the same type of thing for your second order, and so you had 1 over A initial, 1/2. All right, so you plug in that, and that is, then I'm going to subtract 1 over A initial. I'm going to bring that to the other side, and that's equal to K T 1/2. So if you did exactly the same thing that you did for first order, but now we're doing it for second order, which means that my A at time t is exactly 1/2 of my initial concentration of A. And then you do the math. You have 2 over your A initial minus 1 over your A initial, and that is equal to KT 1/2. And you have a common denominator. 2 over A0 minus 1 over A0 is 1 over A0, 1 over A initial. And that is equal to KT 1/2. Then you divide both sides by K. So you end up with your half-life for second order is equal to 1 over your initial concentration of A times T, times K, and that's equal to your T1. All right, so that is right here. All right, so you have your half-life for first order, right? You have your half-life for second order, and then you have your half-life for the zero order. And all of these are done by just doing a substitution. Your A at time t is 1/2 of your A initial. And that's all you're doing is you're putting that in, and then you're solving for it, and then you have your half-life. All right, so now for the second order, it does depend on your concentration of A. So it's 1 over K initial concentration of A. Same for zero order. It depends on your initial concentration of A. First order does not depend on your initial concentration of A. You do not need an initial concentration of A to find the half-life for a first order reaction. All right, so this one tells you that, again, it has both things. You would not need this because it gives you this. All right, so if the K value is given and the units of K will tell you that this is a first order reaction. All right, and so it's first order, you know that by K, and it asks for the half-life. This is an extremely simple question because to get the half-life of a first order equation, you simply take 0.693 and divide by K, which is given as 2.20 times 10 to the minus 5, 1 over seconds. So this is an extremely simple question. All right. And so then the second one is how long in hours would it take for 50% of the SO2Cl2 to decompose? Well, that's the exact same answer. All right. That's what half-life is. That's how long it takes for half of that to decompose. And so A and B are exactly the same question. So sometimes things may look difficult, but they are actually very, very simple. All right, so when you have that many seconds, normally then you would convert into hours. So you convert it, so seconds to minutes, so 60 seconds in a minute. Convert it to hours. So you need to know that there's 60 minutes in an hour. And so the difference is they asked for it in hours, but they didn't ask for A in any units. And I would normally give it in how long is 3.15 times 10 to the 4 seconds. Well, as soon as I put it into hours, I will tell you. It is 17.5 hours. Did it say 2 half-lives? All right. So anyway, they're requiring 2 half-lives. So when your first order, maybe it was not a clear question. So 100% down to 50%. All right. That took 8.75 hours. To go from 50% down to 25% takes 8.75 hours. To go from 100% down to 25% would take 17.5 hours. All right, so every time you cut it in half, it takes 8.75 hours. Every time you're cutting in half. And that never changes for first order. It's every time you're cutting it in half, it takes 8.75 hours because K is a constant and that never changes. So it's always the same. All right, let's do this problem, but this time we're going to do it as a second order reaction. So if I changed this to 1 over molarity times second, or I said this was second order, so now it's second order. All right. Well, all right. So you couldn't do this if it was a second order because in order to get the half-life of second order, it is the half-life is 1 over your initial concentration of A times K. All right. So they did not give an initial concentration. They didn't have to give an initial concentration because it was first order. Now that I'm changing it to a second order, I'm just going to use the same initial concentrations that we had before. 1.65 times 10 to the minus 2 molar is my initial concentration. All right, and so my question is, so this is a bad question. What they wanted to do is, how long in hours would it take for another 50% of the SO2Cl2 to decompose? All right, so I want to know, now that I have my initial concentration and I'm just going to use the same number for K, but I have the new units for second order, is I want to know how long is it going to take to go from 100% down to 50%, and then I want to know how long it's going to take to go down to from 100% down to 25%. And so you take 1 over the 1.65 times 10 to the minus 2 and your 2.20 times 10 to the minus 5. What you're going to find is the next time you do it, you're going to have 1 over K, 1.65 times 10 to the minus 2. That is not your initial concentration for the second time. For the second time, it is half of that, and that is 0.825 times 10 to the minus 2. Now, K is a constant, and it will not change. But your initial concentration is going down by a half each time. So if your first one was 1 hour, the second one would be 2 hours, and your total would be 3 hours. So we will do a second order integrated rate law tomorrow.